Okay, good afternoon, everyone. Let's start. Yeah, so don't forget, we got a quiz will be due on this Friday, right? Don't miss the quiz. Okay, so let us continue with the random variables. In the last lecture, we introduced the definition of random variables. What is random variable? So don't get confused by its a name, right? It's actually not a variable. Random variable essentially is a function which maps from a sample space to real numbers. So basically, you can view like no matter what kind of like random experiment or random things you're interested in, I'm gonna map every possible outcome of your experiment of interest to some real number. And so that I don't need to care really the exact context of your random experiments and so on, right? We just need to look at, after the mapping, what do those numbers look like, and what kind of probabilities, what kind of rules can we summarize all of those mapped numbers, right? So that's called random variables. We give some examples, right? For example, if you roll dice for twice, right? Your sample space would be just pairs of the points, right? 1 point, second point after you're rolling the die, right? And I can define a random variable, which is function, which maps such a pair to a number. This number is the summation of the 2 points in this pair. And there could be numerous ways to define random variables. Here's just one example. You can also define the random variable to be as like I times g, right? Or I minus g, or even I divided by g, right? So there's a variety of way of doing that. So our discussion right now is just limited to discrete random variables, meaning that you're gonna map every element in the sample space to a number, but the number of elements in your sample space is finite. By finite, I means like maybe just 100, maybe just 1,000, but it is finite. For example, in this sum of dice example, you roll the die for twice, right? You got 2 points. And if you just enumerate all possible points from your rolling dice for twice, right? You at most have like 36 pairs of that. So that is finite. When you do the mapping, you can only map to at most 36 values. Right? Sometimes you might have like different pairs through random variable are mapped to the same value. Right? That's fine, right? But later we'll talk about continuous random variables, which are different. In the continuous random variables, one big thing is that the sample space may no longer be finite. Instead, it could be infinite and more complex. It could be uncountable infinite, right? In that case, the random variable is also a function, but you have to add some additional restrictions. I will briefly mention that you should restrict this function to be a measurable function. We're not going to talk about what does mean for measurable function, but just to make sure this additional constraint, just to make sure your definition of random variable makes sense. It won't lead to some contradictory results when you calculate the probabilities out of them. So we mentioned that why do we introduce random variables? One big motivation is that because there are so many random events or random experiments in real world, right? From very, say, from the weather to stock pricing, from country, from like international trading to, scientific experiments. There's so many, right? And people would like to extract some commonly used rules or properties or mathematics underlying all possible randomness, right? That's why we need some like a unified framework to analyze those things. So we map the outcomes of all kinds of random experiments into a real number space. So mathematicians, statisticians only need to focus on this abstractive yet unified space and look at what kind of lemma, what kind of theory can we get out. And then we define with the definition of random variable, we can redefine a lot of events. So we can use the value that a random variable can take to define events. Right? For example, I can define this event, namely the value of the random variable is A. So this defines event in the original sample space as follows. I'm gonna collect all the outcomes in the sample space such that the evaluation of the random variable at such outcome is A. Right? That's a new way to define events. Just by looking at which elements in the sample space can cause the random variable's value to be a specific value A, I define an event. Right? So we need to get used to that because in the future, when we compute the probability or other functions, we often use the most things we're dealing with is just the random variables and the events defined by random variables. Right? So here we also give examples, right? So suppose we look into the sum of dice example again, right? If I define the sum is 5, right? It just means that it is an event that includes all pairs of points in the sample space whose summation is 5, right? Which I counted before, which includes like 1, 4, 2, 3, 3, 2, and 4, 1, right? And similarly, you can also define events like, okay, what if the events represented as like sum s less than or equal to 4? Right? It just represents all the pairs in the sample space whose summation is less than or equal to 4. Right? So when we write the probability over PS less than or equal to 4, it just means what is the probability over this event. Does it make sense? Yeah, we're doing a quick review of what we have discussed in the last lecture. So also we did some practice, like if I define this particular random variable, and if you use different A, we write down what are the explicit events it represents, right? Meaning what are the set of the elements in the sample space represent that event, right? So we're not gonna repeat that, right? Okay, so based on random variables, we start introducing two important functions. But you can view those functions are both a particular type of probability over events, right? So it is only it is only interested in how we're going to construct such type of events, right? So the first function is called a probability mass function. In a continuous value or continuous context, we'll recall it as a probability density function. So what is probability mass function? It is just a probability of a particular type event in the form as x equals to A. So as we mentioned, right, the event x equals to A represents the set of all the elements in the sample space when the random variable evaluated all those elements, it is equals to A, right? So of course, when you vary A, when you change A, right, you're gonna have different events. Right? For example, for the summation of the dice, right? I plus j, right? If you, maybe I can just write it as x ij equals to I plus j, right? So if I look at x equals to 2, it will only have one pair, right? In a sample space, which corresponds to this event, right? So if x equals to 3, you're gonna have two pairs, 1, 2, 2, 1, right? If x equals to 4, you're gonna have more pairs, which we're not gonna enumerate. But it means that if you choose A equals to 2, A equals to 3, A equals to 4, you're gonna have a different events. And the probability of the event also varies, right? So you see, actually there's a mapping between the A you use to define event and the probability of that event, right? So this is called a probability mass function. It's mapping from A to the probability of the event defined by A. Does it make sense? Everyone's comfortable? Okay. So we also visualize like what does the probability mass function look like in the context of discrete random variable. The probability density function should look like this, right? So if you look at x-axis, just all possible values of A, and the y-axis is the function value, right? So you can imagine in this A-axis, you're gonna pick up a set of values A who gives non-zero probabilities, which are the non-zero probability mass function values, right? For all the other A values whose corresponding event has a zero probability, then the mass function, the probability mass function should be zero as well. That's why when you look at this PMF, it should be like discrete vertical lines, right? Like for example, I mean, if you feel uncomfortable, like why FA could be zero, right? Consider you take A equals to 17, right? Let us look at what is this event represent, right? Which pair of the points in a sample space can lead the random variable's value to be 17? No, right? Because at most, each point can take, up to 6, right? You add them together, you got 12, right? You will never have any pair of points whose summation gives 17. So actually, this represents an empty event or impossible event whose probability is 0. That means the PMF at A at 17 is 0. That's why you see in this axis, where many A values will have the PMF value being 0. Okay. Any questions so far? Okay, and then we have another common use function in probability theory. It is called cumulative distribution function, CDF, right? So CDF is also another type of is another is a probability for another type of events. So in this type of event, it's not like, okay, what is the probability of x equals to A? It's the probability of x less than or equal to. So you see, there's just one more less in the inequality. So you kind of turn the equation becomes an inequality, right? Then this function has a huge difference from the probability mass function. Right? So we want to look at first, what does the event x less than or equal to A represent? As the name suggested, it just represents all the samples, I mean, all the elements in the sample space. When you evaluate such an element with your random variable x, the value will be less than or equal to A. That's it. So in our previous case, we're going to look at when you evaluate x at this element omega, the value should be exactly A, right? But now we want the value to be less than or equal to. And of course, this event won't be the same as this event, right? Therefore, the probability won't be the same as well. Right? A quick review, right? We can just write out some like example, right? For the sum of dice example again, right? If I roll the die for twice, right? I define my random variable as their summation. Right? So the event, suppose you choose A equals to 5, right? Then what does this guy mean? What kind of elements in the sample space are included in this event? Yes, exactly, right? We can just enumerate manually, which is a little bit tedious, but it's good. It's a good tedious practice, right? So you can just look at all pairs of ij whose summation is less than or equal to 5, right? So we can start with 1, 1, 1, 2, 1, 3, 1, 4, right? Could it be possible for 1, 5? No, why? Because summation is bigger than 5, right? It doesn't satisfy the inequality. So then we start with 2, 2, 1, 2, 2, 2, 3. Do we have 2, 5? No, right? Okay. Start with 3, right? 3, 1, 3, 2, right? Do we have 3, 3? No, right? 3 plus 3 is 6. It's bigger than 5, right? And eventually 4, 1, right? So we won't have 5, 1 because 5 plus 1 is bigger than 5. Right? So this is the event x less than equal to A represent, right? And in contrast, what is the event x equals A, right? Here A is 5. What is that? Anyone can name it? Yes, right? In this case, like you're gonna pick up all pairs whose summation is exactly 5, right? Rather than less than 5, right? So if you look at, it's actually included in the or contained in x less than equal to 5, right? You can circle them out, right? 1, 4, 2, 3, 3, 2, and 4, 1. So you can see this event, I mean, x equals to 5 actually is a subset of the event x less than equal to 5. Right? 1, 4, 2, 3, 3, 2, and 4, 1. Okay. So you see that actually, usually the probability mass function should be upper bounded by the cumulative distribution function, CDF, right? Okay, any question regarding the definition of the CDF? Okay, so what does the CDF look like if we visualize them? So this is a little bit different from PDF, I mean PMF. But the CDF is more like accumulate. That means when A is enough large, you know, X less than equals to A will always true, right? That means all sample space, the whole sample space, all elements in the sample space, they will satisfy this inequality. That means as long as A is enough large, the CDF will simply be 1. Right? Imagine if this guy corresponds to the whole sample space, then the probability for this whole sample space is what? It's just 1, right? So that's why it's more like accumulate all probability density functions along with A. So typically, like for example, if you got PMF, like to be something like this, right? So I'm just write down 3, say A just equals to 1, 2, 3, and the PMF is 1/3 for every value of A, like 1, 2, 3, right? But if you look at the CDF, you see that before 1, will be simply 0. Why? Yes, exactly, right? So as we mentioned, in this case, you have only 3 values. F1 equals to 1/3, F2 equals to 1/3, F3 equals to 1/3, right? So that means when A is less than 1, right, there won't be any elements in the sample space whose evaluation is less than 1, right? The minimum value of the random variable you can get is 1. So that will correspond to an empty set whose probability is simply 0. Right? That's why when we draw the CDF curve, you see less than 1, it will be 0. Okay, so how about from 1 to 2? What's the CDF value? It's just 1/3, right? Because if you look at X less than equal to 2, no, actually not to 2, like less than equal to something, like A is less than 2, right? You know there only be one element in the sample space which satisfies this guy, right? Which is the element that correspond to the 1 of the random variable value. Right? So this guy will be 1/3, right? Okay. yeah, maybe I should be more clear. Let us just explicitly write it out. Like I got x omega 1 equals to 1, x omega 2 equals to 2, x omega 3 equals to 3, right? And I know the whole sample space just has three elements, omega 1, omega 2, omega 3. Is it better? Is it more clear? Right? So we know that, okay, if A is less than 1, right? We know there won't be any elements in the sample space, like omega 1, omega 2, omega 3, they all cannot give you the value of x to be less than 1, right? So that's why less than 1, when A less than 1, this CDF value will be 0, right? But then if A is less than 2, but no less than 1, right? 1 less than or equal to A and less than 2. Like, for example, A could be 0.5, 1.5, right? If you look at this, you see that x less than or equal to A in this case will simply be what? Simply what? Yeah, the even is just 1, right? Because so the even will be just omega 1, right? Because there is only one element in the sample space whose random variables value is less than, say, 1.5, right? Which is just 1. Does it make sense? Right? So now, if we look at 2 less than A, no less than A, and less than 3, right? What's the CDF function? So we can take a look at it. For example, if I put A equals 2.5, right? So what is the event S less than or equal to 2.5, right? What's that? Which elements in the sample space are included? 1 and 2, right? Because both omega 1 and omega 2, because at both omega 1 and omega 2, the random variables value is less than or equal to 2.5, right? So then the probability of this guy will be what? 2/3, right? You just add, you got two elements in the sample space. Your elements only have 3 elements total, right? So the probability of this even is 2/3, right? So you see that this guy will be 2/3. Does it make sense? Right? Okay, and the last range we want to look into is that when A is bigger than 3 or equal to 3. So what does this even represent? Or which elements in the sample space are included in this event? Yeah, all of them, right? All omega 1, omega 2, and omega 3, right? Why? Because if you look at the random variable value at all those omegas, they're all less than or equal to 3, right? And then what is the probability for this event? What's the probability for this event? No one guess? It's just 1, right? Because the whole sample space, right? It's a probability over the whole sample space is always 1 because it's a definitely happen event, right? Right. So that means when A is bigger than or equal to 3, you're gonna have 1 forever. So you see, it's very different from the PMF here, right? Right? It's more like, okay, I'm gonna accumulate the PMF at every point. At every point, every input to the CDF, it sounds like I'm accumulating the PMF from every value below this point, right? Add them together to get the CDF function. Right? That's the intuition. Right? That's why it is called a cumulative distribution function. And if we switch to continuous random variables, then it won't be summation. It will become integration, right? Everyone should have you guys should be very familiar with integral, right? It's just a limit of summation over infinitesimal regions, right? It's just a extension or generalization of summation. Okay, any question regarding the definition of the CDF? Okay, so next we're gonna just do some a little bit of practice to make our get more familiar with this definition, because in the future, these two functions, PDF and CDF, are at the cornerstone of the probability theory, the statistical hypothesis testing, significant tests, all kind of stuff. Right? So we should be we need to be very comfortable in using those definitions, right? So the first example I want to practice is just like simple extension of what we have discussed, right? One dice experiment, meaning that I just roll the dice for once. Right? You just look at a point. And of course, you've got equal chance to see every possible point from 1 to 6. So obviously, your sample space is just 1, 2 to 6, right? And our random variable is an identity mapping, meaning that given my point, given the input point, I'm just use that input point as my output. Okay, so the first question, what is the probability mass function? How many non-zero values do we have for the probability mass function? How many? How many non-zero values for PMF? Just 6, right? Because you can only choose 6 possible values which maps the original elements in a sample space, right? So the PMF is straightforward. We got Px I. Probably I'm gonna ignore this. Px equals to A is 1 over 6 for A is 1, 2, 3 until 6. Does it make sense? Right? So if we draw the figure of the PMF, it's A, right? We actually got 6 possible values, which give you non-zero PMF. They all view them as 6, right? And for all the other A values, the PMF is simply 0, right? Right? Yeah, if we can double check, right? If you take x equals to 1.5, right? To know the PMF, we need to know what is the event it represents, right? So what is event? Represents x equals to 5, 1.5. It's empty set, right? Because you cannot find any element in the sample space which give you the random variable value is 1.5. So it is simply empty. That means the probability is 0. Right? Okay. So now let us calculate the CDF. So the CDF, we can also consider 1, 2, 3 until 6, right? So let us consider different ranges of A, right? This is 1, 2, 3, 4, 5, 6, right? So we can partition the range of A according to those numbers, right? So the first, the range is A less than 1, right? So for A less than 1, if you want to know the CDF value, namely big FA, right? So we need to know, okay, what does this event represents, right? What event represents A less than 1? Any thought? No, it's just empty, right? Because we just look at the sample space. You want to say at which set of the elements in your sample space such that your random variables value is less than A, less than or equal to A. When A is less than 1, you'll find no one, right? No element in the sample space will give that, because the X's value is at least 1, right? When A is less than 1, no X value will be below 1. Okay, so in this case, this event is just an empty, even impossible event. So your FA will be P of X less than or equal to A. Sorry, I should write it more clearly. To look at what is X less than or equal to A. This is empty, right? So this event is an impossible event, so the probability is 0. That means your CDF value is 0. Right? So right. Okay. So the second range will be between 1 and 2. Right? So 1 less than equal to A but less than 2. So again, we want to look at the CDF value. We need to look at what does this event represent, right? What's the event? I heard that. Yeah, it just contains one element, 1, right? Because A is less than 2, right? For example, A is 1.5 or A 1.9, right? You know, among all the whole sample space, there's only one element which has the X value to be less than 1.5, 1.9, which is just 1, right? So in this case, we only have one element in the event, so the probability of Px less than or equal to A will simply 1/6, right? So we enjoyed it will be something like this, right? This is 1/6, right? So I mean, keep doing this. if we look at 2 less than equal to A and less than 3, and again, we want to look at what does this event represent, right? X less than equal to A. What does this event represent? Which outcomes of your rolling the die would be included in this event? 1 and 2, right? Because A is bigger than no less than 2, right? But it's less than 3, so this event will only include 2 elements, 1 and 2. So the probability also is a CDF value at A will be 2/6, right? It's 1/3, right? So I'll use another color. Four, 6, right? We can continue, right? For three less than A, less than equal to A, but less than 4. What does the event X less than equal to A represent? What's that? Any thought? The A is between 3 and 4. Of course, it's a half interval, meaning it doesn't reach 4 actually. So then what does the event X less than equal to A include? What kind of outcomes are included? 1, 2, 3, right? Yeah, I mean, again, you just use definition, right? You say when you use 1, 2, 3, the X value will be 1, 2, 3. They're all less than equal to A, right? So it is sorry, 1, 2, 3. So the CDF function is the probability of this event, which is 3/6, right? Any question? Okay. So in this guy, we're gonna jump again. Right? So we got 3/6, right? Okay, so we can continue, right? I mean, it's a little bit tedious, but it's good for us to use that to practice our understanding, right? So when 4 less than equal to A, less than 5, then this event X less than equal to A will include a 1, 2, 3, 4, right? So the CDF will be 4/6, right? So six, 4/6. Well, the remaining is kind of repeat, right? So when A is between 5 and 6, it would be 5/6. 5/6. And when A is bigger than 5, what does this even represent? What if A is bigger than 5? What does the event X less than equal to A represent? Oh, sorry, so yeah, it includes all the 6 points, right? It includes 1, 2, 3. Yeah, we should think about it's a 5. 5 less than a and 6. It will include 1, 2, 3, 4, 5, right? But eventually, when a is bigger than 6, it will always include all the 6 points, right? This is 1 through 6. Then the probability, then what's the probability? It's just 1, right? So that's why eventually you will see a constant 1 beyond a equals to 6. That's what this CDF function look like, right? It's like a step function. You're going step by step, kind of like accumulate all the PMF values up to the input, right? Okay, so let's take a 5 minutes rest. Just for homework. Sure. Yeah, yeah, that's right. The logic part, I'm not checking
Okay, the
numbers.
math, yeah,
Yeah. You just need to use the definition of the,
right, so
Yeah,
these
yeah.
are equal minutes.
yeah.
Okay, thank you.
Okay, so let us continue. So here we just give one tedious example to show what's the meaning for CDF, right? What's the difference between CDF and PDF? And if you want to practice more, there's one more problem. I listed here, buried by these markers. So like consider like you two dice experiment, or you roll the die for twice, right? The same. No, a different random variable, xij equals to I plus j, right? Then try to calculate the PDF and the CDF. It's a little bit tedious, but it's a really good practice. And one thing you should be very careful is in here, like for xij equals to 5, say. And then the events, the underlying event can include multiple pairs of points, right? For example, 1, 3, sorry, 1, 4, 4, 1, 2, 3, 3, 2, right? It can vary. So the probability mass function won't be this kind of equally length standing matches, right? It's not like that, right? Okay, so based on the probability mass function and probability and a cumulative density function, we can define a lot of distributions, right? So that actually those distributions can be used to describe a lot of like phenomenon in practice. The very first distribution we would like to discuss is called Bernoulli distribution. Right? So what is Bernoulli distribution? Bernoulli distribution is defined by a particular type of PMF. So it's very, very simple PMF. So first, it assumes that your random variable can only take two possible values, 0 or 1. Okay. And second, we require that the PMF takes the following form. The value of the PMF at 1 is some small positive number, p, which is between 0 and 1. And then the value of the PMF at 0 is 1 minus p. Right? So here, this is a small lowercase p is not a probability function. It's just a single number between 0 and 1. This probability mass function defines the so-called Bernoulli distribution. Any question regarding definition? Okay, so in some literature, you might see a more uniform form for this, right? So you might see Bernoulli distribution, they express the PMF in this way. Fx equals to p to the power of x, 1 minus p to the power of 1 minus x. Why is this correct? Or why is this equivalent? Any thought? Why this form is the same as this form? Yes, exactly, right? So this is just a more succinct form, right? So if you just really look at the value, right? So we know, as we mentioned, right? The Bernoulli distribution requires that your random variable can only take values 1 or 0, right? So if you can take a look at if x takes a value 1, right? When x equals to 1, so this whole thing, right, will becomes p, right? Because x to the p to the power of x, which x is 1, where x is 1 is p, right? And 1 minus p to the power of 1 minus x here will become 0, right? which is simply 1. And if we take x, the value of x to be 0, what happened? So you know, if you look at this form again, right, it becomes p to the power of 0, 1 minus p to the power of 1 minus 0, which is 1 minus p, right? So you see, it goes to this second case, fx 0 equals to 1 minus p. Does it make sense? Any question? I mean, this I mean, these two definitions are interchangeable, right? And in many mathematical derivations, you may see this one is more often used because they are very easily to be combined with other, you know, continuous probability mass functions together to calculate things. So, I mean, next time if you see this form, don't get surprised or get confused. Okay, so if a x is a random variable with this particular PMF, we say x follows a Bernoulli distribution, or x is a Bernoulli random variable with parameter p, right? So we often use this notation, x this tilde, and that means it follows Bernoulli with parameter p. So what does it mean, right? So a very concrete experiment you can associate with Bernoulli distribution is flipping a coin, right? Right. So you can view like you see the heads up as a success, which means that your random variable value takes 1. And when you see tails up, right, you can view it as kind of failure. And your random variable then takes value of 0. So basically, Bernoulli distribution can describe the experiment that you flip a coin with the probability p of saying heads and probability 1 minus p of saying tails. Does it make sense? That is what Bernoulli examples of Bernoulli distributions usually are introduced. But of course, you can use that to represent many random experiments with only binary outcomes. Like for example, if I pass the exam or not, right? If I got A or not, if I find a job or not, or if I get up before 7 a.m. or not, right? So basically you can use Bernoulli distribution to characterize or model any random things or random events that only has binary outcomes. Any question regarding the definition of Bernoulli experiment? A Bernoulli distribution? Okay, great. So now, Bernoulli distribution, sometimes people call it Bernoulli trial, just represents one experiment, right? You say whether you see some binary outcome, whether you see success or say failure, right? But what if you try this multiple times, like flipping a coin, right? And flipping coin for once, I got say 60% chance of saying heads up and 40% chance of saying tails, right? But then what if I just keep flipping the coins for 10 times? Then what is the distribution of the outcomes of the whole 10 times flipping? So This extension of Bernoulli distribution is called binomial distribution. So what is binomial distribution? So binomial distribution describes the probabilities of repeated Bernoulli trials, such as flipping a coin 10 times in a row. Right? And here we make very simple assumption. We assume each trial is independent of the others. Like you flip a coin the first time, you flip a coin the second time, the result of second time has nothing to do with the first time. Or the result of any trial is independent of all the previous trials. Then we would like to know, okay, because now suppose you flip a coin for 10 times, right? Your outcome is not just binary, right? It's just a list of either heads, tails, or sequences, right? So then we would like to use this binomial distribution to characterize what is the probability for different possible sequences of the results. Okay, so in general, the binomial distribution is characterized by two parameters. One is n, one is p. N is just the number of trials, like how many times you're gonna flip the coin or toss the coin. And p is the probability of success for each trial. Like in our coin experiment will be just the probability you see the heads up. Right? And then the random variable associated with binomial distribution is defined as the total number of successes from n trials. By success, I mean, say, total how many times you can see the number of heads, right? So now my question is, what are the possible values X can take? What possible values can X take? Yeah, it's a finite number, but what is the maximum finite number? What's the minimum finite number? Can X take to be -1? Can X to be take like 1 million? 0 to n, right? So X could be 0, 1 until n. Why? Yeah. So your answer is absolutely correct. Let me just explain, right? So first, the total number of successes, you can see 0, right? Imagine it might be possible that you're such a bad luck, right? You toss the coin for 10 times, you never see heads up, right? But your X cannot be below 0, right? Because you cannot see -1 success. But the number of success cannot exceed n, right? You toss a coin for 10 times, you cannot see 11 heads, right? You cannot see 100 heads. So the best luck will be, okay, every time you toss a coin, you see heads, right? So that means at most you can have n successes. That's the range of the values X can take, right? Anything outside this range is infeasible. Okay, any question regarding the definition of binomial distribution so far? Okay, so then the next question is that, suppose I have such a random variable that follows the binomial distribution with n and p, right? N trials and the probability of success p, right? How to compute the PMF, right? As we mentioned, X can take value from 0, 1, up to n, right? So then that means like we would like to compute the probability mass function value, namely the probability of X take each possible values, right? A is 0, 1, until n, right? Okay. So to show this, right, let us consider a special case. Suppose n is just 5. I toss a coin, a flip a coin for 5 times, and my probability of success is 0.5. And let us consider the probability of x takes 1, right? So what's the probability of x takes 1? The answer to that might be not that explicit, right? But let us just follow definition. This is talking about the probability of the event x equals to 1, right? So what does this event include? Yeah, go ahead. Yeah, but here is a little bit complex than that. Because remember, now we're flipping the coins for 5 times, 5 independent tossing, right? And overall, you only see 1 heads up. Then we want to look at, okay, this x, which is the total number of the heads, right, or successes, is what, right? We need to see what does the underlying event look like. Yeah, that's the right direction, right? Because remember, we're doing n trials, right? That means your sample space won't be just a single outcome. It's a sequence of outcomes of all the experiments, right? So it will be something like this, right? You want to look at the outcome of first is heads, maybe second is tails, heads, tails, something like that, right? You actually have an array of outcomes, right? 5 outcomes give 1 element in the sample space, right? If you write it in a more formal way, your sample space should be something like this, right? So it's S1, S2, S3, S4, S5, right? And each S1, 2, 3, 5 represents whether in the corresponding flipping you see heads or tails, right? So this guy could be highest tail. This guy could be highest tail. And everything, every item could be heads and tail, right? And how many elements do we have for the sample space? Just 5. I mean, sample space are the total number of the outcome sequences of these 5 trials, right? How many do we have? 25 is still inaccurate. Yeah, it's 2 to the 5, right? So remember, you're gonna enumerate all possible values of these five outcomes, right? S1 to S5. So I'm gonna use SI, which belongs to either heads or tails, right? So each outcome have 2 possible outcomes, right? 2 possible results, heads or tails, right? So you have 5, then the total number will be 2 to the power of 5, right? Does it make sense? Now, let us look at the event defined by x equals to 1. Can you name the sequences contained in this event? Yes, exactly, right? We just enumerate all sequences which only contains 1 head, right? But that head might appear in the first time or second time, or third time, or fifth, or fourth time, or fifth time, right? Actually, you have 5 sequences, such sequences, right? This one will be, I'm just use 1 to represent paths, right? To be more concise, right? 0, 0, 0, 0, or 0, 1, 0, 0, 0, or 0, 0, 1, 0, 0, sorry. Or 0, 0, 0, 1, 0, or 0, 0, 0, 0, 1, right? We got 5 sequences, right? So now, to calculate the probability, right, for this event, right, we just want to look at the probability for each single sequence. What's the probability for each single sequence? Say 1, 0, 0, 0, 0. What's that? What? Yeah, that's correct, right? But what if we write it in a way that involving the parameter p? Say, suppose you toss a coin and you got the chance of p to see the heads. Of course, you got chance of 1 minus p to see the tail, right? The p is not necessary to be 0.5. Can we come up with a formula to represent the probability of seeing this sequence? Any thought? Remember, each experiment is independent, right? So you just say one head, right? So the probability of saying one, yeah. Yeah. Well, I mean, let's just come out this formula in terms of p, right? Yeah. So you can imagine like through this sequence, right? For this guy, right? You only see one head, right? So the probability of you seeing one head is just p, right? And then the probability, what about the probability you see all 4 tails? Yes, exactly right. Remember, you toss a coin independently, right? You see, the first time you see a heads, right, with probability p, right? The second time you see the 0 tail with probability 1 minus p. Third one, you see the tail with 1 minus p probability, and last, fourth one, 1 minus p. Last one, 1 minus p, and summarize is p times 1 minus p to the power of 4, right? Does it make sense? Right? And similarly, when you calculate the probability of the second sequence, what's that? It's the same, right? So you see that actually for every sequence in this event, they have the same probability. You have 5 sequences in this event, then add them together, you got your probability of x equals to 1, which is 5 times p to the power 1, 1 minus p to the power of 4. Okay, let's stop here today, and we'll continue with binomial distribution in the next lecture.